January of 2026, a team of physicists in Vienna did something that should bother you. They took a clump of sodium metal, a tiny speck containing roughly 7,000 atoms, and they put it in two places at the same time. Not figuratively, not as a metaphor, not in the way that you might say you left your keys in two places because you can't remember which counter you dropped them on. They created conditions where this object, this lump of metal with a physical size you could measure, existed in a genuine quantum superposition. Its position was not uncertain in the classical sense of we don't know where it is. Its position was undefined. The clump of metal did not have a location. It had locations, plural, spread across a gap more than 16 times wider than the particle itself. And when they ran the experiment thousands of times, the results produced an interference pattern that is physically impossible unless each individual particle traveled through the apparatus as a wave, sampling multiple paths simultaneously before arriving at the detector as a single dot. This is the largest object ever demonstrated to behave this way. And the fact that it works, that quantum mechanics holds at this scale with zero detectable deviation from theory, is one of the most consequential experimental results in modern physics. It tells us something unsettling about the nature of reality. It puts direct pressure on theories that predict quantum mechanics should break down before you reach objects this big, and it moves us measurably closer to answering a question that has haunted physics for a century. Where does the quantum world end and the classical world begin? The answer, as far as anyone can tell from the data, is that it doesn't. But before we can appreciate what the Vienna team actually did and why it matters so much, we need to talk about the experiment that started all of this, the one that Richard Feynman called the only mystery of quantum mechanics, the double-slit experiment. You've probably heard of the double-slit experiment, at least in outline. It's one of those things that gets referenced constantly in popular science, usually with some breathless narration about how bizarre quantum mechanics is. But it's worth going through carefully, because the details matter, and because the specific thing that makes it strange is also the specific thing that the Vienna experiments are testing at unprecedented scale. Here's the setup. You have a barrier with two narrow slits cut into it, side by side. On one side of the barrier, you have a source that fires particles at it. On the other side, you have a detector, something like a photographic plate that records where each particle lands. If you fire bullets at the barrier, say from a machine gun that shakes a bit so the bullets go in slightly random directions, what happens is straightforward. Some bullets go through the left slit, some go through the right slit. Most hit the barrier and stop. The ones that make it through pile up behind each slit in two overlapping clusters. You get two blobs on your detector, one behind each slit, fading out at the edges. This is exactly what you'd expect from particles traveling in straight lines through one slit or the other. Now do the same thing with water waves. Send a wave front at the barrier. It hits the two slits, and each slit becomes a new source of circular waves spreading out on the other side. These two sets of waves overlap, where the crest of one wave meets the crest of another. They add up, and the water is higher. Where a crest meets a trough, they cancel out and the water is flat. The result is an interference pattern, alternating bands of strong waves and calm water, fanning out across the detector surface. This is what waves do. It's the signature behavior that tells you something is a wave and not a stream of particles. Here's where it gets strange. Fire electrons at the double slit, one at a time, slowly enough that each electron hits the detector before the next one is even launched. You would expect each electron to go through one slit or the other, just like a tiny bullet, and gradually build up two blobs on the detector. After all, an electron is a particle. It has mass. It has charge. When it hits the detector, it arrives at a single point, making a single dot. But that's not what happens. After you've sent thousands of electrons through, one at a time, the dots on your detector don't form two blobs. They form an interference pattern, alternating bright and dark bands, exactly like the water waves. Think about that for a second. Each electron arrives as a single dot, at a single point, like a particle. But the pattern they collectively form is the signature of wave interference. And this pattern includes dark bands, places where electrons almost never land. If each electron just went through one slit or the other, there would be no reason for those dark bands to exist. The only way to produce them is if something from both slits is interfering. Waves going through both slits simultaneously create regions where they cancel each other out. That is the only physical mechanism that produces dark fringes. So each electron, individually, must somehow be going through both slits, not some electrons through the left and some through the right, with the statistics working out. Each electron, by itself, carries information about both slits. It interferes with itself. And if you try to catch it in the act, if you put a detector at one of the slits to see which one the electron actually goes through, the interference pattern vanishes. You get the two-blob pattern you'd expect from particles. The act of determining which path the electron took destroys the very thing that made the pattern interesting. This is not a thought experiment. It has been performed thousands of times, with electrons, with photons, with neutrons, with atoms. The results are always the same. Quantum objects exist in superposition, simultaneously exploring multiple possibilities until something forces them to commit to a definite state. And the evidence for this superposition is the interference pattern, because interference is the smoking gun. It is the thing that cannot happen if the particle took only one path. Now here's the question that has driven an entire subfield of physics for the past 100 years. How big can the object be before this stops working? The idea that matter has wave properties wasn't always obvious. For most of human history, the distinction between particles and waves seemed clear. Particles are things. They have locations. They bounce off each other. Waves are disturbances. They spread out. They interfere. A rock is a particle. A ripple on a pond is a wave. These were entirely separate categories. That changed in 1924 when a French physicist named Louis de Broglie submitted a doctoral thesis that his advisors didn't quite know what to do with. De Broglie proposed that everything, every object with mass and momentum, has an associated wavelength. Not just light, which had been shown to behave as both wave and particle by Einstein and Planck. Everything, electrons, baseballs, you, the Earth, all of it. The relationship is simple. The wavelength equals Planck's constant divided by the momentum of the object. Planck's constant is a tiny number, 6.6, 2, 6 times 10. to the negative 34th joule seconds. The momentum is mass times velocity, so the wavelength depends on how heavy the object is and how fast it's moving. Heavier and faster means shorter wavelength. For an electron moving at typical speeds in an atom, the wavelength works out to roughly the size of an atom. That's why electron microscopes work. The electron's wavelength is small enough to resolve structures that visible light, with its much longer wavelength, simply can't see. For a baseball thrown by a major league pitcher, the wavelength works out to about 1.1 times 10 to the negative 34th meters. To put that in perspective, the smallest meaningful length in physics, the Planck length, is 1.6 times 10 to the negative 35th meters. A baseball's de Broglie wavelength is about 3 times the Planck length. It is, for all practical purposes, zero. There is no apparatus in the universe, no conceivable experiment that could detect wave behavior in a baseball. The wavelength is simply too small relative to the object. For a human being walking at a normal pace, the wavelength is about 10 to the negative 36 meters, smaller than the Planck length. Meaningless. For the Earth orbiting the Sun, it's about 10 to the negative 63rd meters. To call that number small doesn't begin to capture it. If you took a single proton and expanded it to the size of the observable universe, the Earth's de Broglie wavelength would still be far too small to detect within that expanded proton. This is why we never see quantum effects in everyday life. It's not that big objects aren't quantum mechanical. According to the math, they are. Every object in the universe has a de Broglie wavelength. But for anything you can see or touch, that wavelength is so absurdly, incomprehensibly tiny that its wave nature is completely undetectable. The quantum behavior is there in principle, but it's buried under so many decimal places that it might as well not exist. De Broglie's thesis committee was skeptical. To put it mildly, they sent it to Einstein, who reportedly called it quite interesting and supported the idea. De Broglie got his PhD. 3 years later, in 1927, Clinton Davison and Lester Germer at Bell Labs accidentally proved him right. Davison and Germer were studying how electrons scatter off nickel surfaces. During the experiment, their vacuum system developed a leak, which oxidized the nickel target. To fix it, they heated the nickel to high temperature, which inadvertently created large, single crystals in the metal. When they resumed the experiment with this modified target, they found something unexpected. The electrons scattered from the surface produced a pattern of bright and dark spots, a diffraction pattern, the exact same kind of pattern that X-rays produce when they scatter off crystals. The crystal lattice of the nickel was acting as a diffraction grating, and the electrons were diffracting off it as waves. The spacing of the pattern matched de Broglie's predicted wavelength perfectly. Davison shared the 1937 Nobel Prize in Physics for this discovery. Electrons were waves, or rather, electrons had wave properties. The distinction between particles and waves, which had seemed so fundamental, was dissolving. But here's the thing: electrons are tiny. They're the lightest particles with meaningful mass that we commonly deal with. An electron weighs about 9.1 times 10 to the negative 31st kilograms, showing that something that's small has wave properties is surprising, sure, but it doesn't exactly threaten our everyday intuitions. You weren't going to run into an electron on the street and be shocked by its wave behavior. The real question, the dangerous question, was whether this wave nature extends to bigger, more complicated objects. Objects made of many atoms stuck together. Objects that start to look, if you squint, a little bit like the things we encounter in daily life. And for decades, nobody could answer that question experimentally. The technology simply didn't exist. That changed in 1999 in a physics laboratory at the University of Vienna. And it changed because of a molecule that looks like a soccer ball. Buckminster fullerene, also known as C60, is a molecule made of 60 carbon atoms arranged in a hollow sphere. It's shaped exactly like the geodesic domes designed by architect Buckminster Fuller, hence the name. Each molecule has 12 pentagonal faces and 20 hexagonal faces, identical in topology to a soccer ball. It was discovered in 1985, and it won the Nobel Prize in Chemistry in 1996. By the late 90s, it was one of the most studied molecules in chemistry. What nobody had done yet was ask whether a whole C60 molecule could behave as a wave. Marcus Arndt and Anton Zeilinger decided to find out. Arndt was a young postdoctoral researcher who had joined Zeilinger's group in 1997, specifically, as he later described it, to jointly start the field of macromolecule interferometry. Zeilinger was already one of the most prominent quantum physicists in Europe, known for groundbreaking work on quantum entanglement and quantum teleportation. He would go on to win the 2022 Nobel Prize in Physics for that entanglement work. But in the late 90s, he was also interested in a different question. How far could you push the double-slit experiment? The challenge was immense. A C60 molecule weighs 720 atomic mass units. That's about 1,300 times heavier than an electron. Its de Broglie wavelength, at the velocities they could achieve, would be roughly 1 to 5 picometers. That's about 1/100th the diameter of a single atom. The wavelength they needed to detect was smaller than the atoms the molecule was made of, by a lot. A standard double-slit experiment was out of the question. To see interference fringes in a regular far-field setup, you need slits roughly comparable to the wavelength. Slits 1/100th of an atom wide don't exist. They needed a different approach. What they used was a diffraction grating, a silicon nitride membrane with a series of parallel slits, each about 50 nanometers wide, spaced 100 nanometers apart. The molecules would pass through multiple slits simultaneously, and if they had wave character, the waves from adjacent slits would interfere with each other, producing a characteristic pattern at the detector downstream. On October 14, 1999, they published the results in Nature. It worked. The Buckminster fullerene molecules, heated to about 900 Kelvin in a small oven, flew through the grating and produced clear interference fringes on the detector. The pattern matched quantum mechanical predictions. 60-atom carbon soccer balls were behaving as waves. This was a genuine shock to many physicists, not because they doubted quantum mechanics in principle, but because of how far removed these molecules were from simple particles like electrons. A C60 molecule has 174 internal vibrational modes. It's a warm, jiggly, complicated object with a rich internal structure. It was rotating, vibrating, and carrying a lot of thermal energy. And yet, its center of mass, the position of the molecule as a whole, was showing quantum coherence. The internal complexity didn't matter. The quantum behavior persisted. Think about what that means. A molecule with 60 atoms vibrating madly at 900 Kelvin, which is hot enough to glow dull red, passes through a grating as a wave. Each molecule individually interferes with itself. It goes through multiple slits at once. It has no definite position in the grating. It exists for that brief moment as a smeared-out probability wave, despite being a relatively massive, structurally complex, thermally excited ball of carbon. And then it hits the detector as a single particle at a single point. This result opened the door to a new experimental program. If 60 atoms could show wave behavior, what about 100, 500, 1,000? Where exactly did this stop? Arndt and his growing team at Vienna set out to find out, and they've spent the past quarter century pushing the boundary steadily upward. The progression from 1999 to the present day reads like a campaign of systematic escalation. Each advance required two things. First, the physicists in Vienna needed better, more sensitive interferometers that could detect interference at ever smaller wavelengths. Second, they needed molecules, bigger and bigger molecules, specifically designed to be both massive enough to push the quantum boundary and volatile enough to form molecular beams in a vacuum chamber. That second requirement meant collaborating closely with synthetic chemists, particularly Marcel Meyer and his group at the University of Basel, who became the molecular architects of the entire enterprise. The problem with simply using bigger versions of C60 is that most large molecules aren't volatile. They don't evaporate easily. If you try to heat them up to create a beam of gas phase molecules, they decompose before they sublimate. So Meyer's team had to design and synthesize custom molecules built to specific mass targets with chemical structures that would let them survive being heated into the gas phase. They decorated massive molecular frameworks with fluffy fluorinated side chains that made them evaporate at lower temperatures. It was molecular engineering in service of fundamental physics. In 2003, the Vienna group demonstrated interference with fluorinated fullerene C70F48, a molecule with 118 atoms. Then tetraphenyl porphyrin with 78 atoms, which was notable because porphyrins are biological molecules, the building blocks of hemoglobin and chlorophyll. A biomolecule was showing quantum wave behavior. By 2011, they had reached 430 atoms. The molecule, a functionalized porphyrin derivative called TPPF152, weighed 6,910 atomic mass units. The interference fringes were measured using a Kapitsa-Dirac-Talbot-Lau interferometer, a significant upgrade from the original far-field grating approach. We'll come back to how this works, because the interferometer design is actually one of the most clever parts of the whole story. In 2013, they hit 810 atoms with a molecule whose formula reads like an organic chemistry exam question. C284, H190, F320, N4, S12. Mass, 10,123 atomic mass units. Over 10,000 AMU, 10 times the mass of the original buckyballs, still showing interference. Then came 2019, and the biggest jump yet. The molecule this time was a functionalized oligoporphyrin, which is essentially a chain of porphyrin rings decorated with fluoroalkyl groups. Its molecular formula was C707, H260, F908, N16, S53, ZN4. Nearly 2,000 atoms, over 40,000 protons, neutrons, and electrons combined. It weighed more than 25,000 atomic mass units, 25 kilodaltons. This is the mass range of small proteins. Insulin, the hormone that regulates your blood sugar, weighs about 5,800 daltons. This molecule was more than 4 times heavier than insulin. The experiment was published in Nature Physics in September 2019, and it required a purpose-built interferometer 2 meters long. The molecules flew through the apparatus in about 7 milliseconds, maintaining quantum coherence the entire time. Their de Broglie wavelength was just 53 femtometers. To put that in perspective, an atomic nucleus is about 1 to 10 femtometers across. The wavelength was comparable to the size of an atomic nucleus, but the molecule itself was hundreds of times larger. The interference fringes exceeded 90% of the maximum possible visibility, meaning the quantum behavior was nearly perfect. This result held the record for 6 years. But the 2019 experiment, as impressive as it was, still used single molecules, carefully designed, custom synthesized, one-of-a-kind molecules. Each one was a specific chemical compound with a defined structure and formula. What the Vienna team did next was different in a fundamental way. They stopped using molecules entirely. In January 2026, Marcus Arndt's group published a paper in Nature that changed the game. Instead of custom-designed molecules, they used sodium nanoparticles, clumps of sodium metal, not precisely defined chemical structures with elegant molecular formulas, but blobs, little balls of metal containing somewhere between 5,000 and 10,000 atoms, with a mean of around 7,000. The particles were roughly 8 nanometers in diameter. To put that in scale terms, 8 nanometers is about 40 atoms across. You could line up roughly 12,000 of these particles along the width of a single human hair. They're far too small to see with a regular microscope, but they're getting into the range where you can image them with an electron microscope. They're not molecules anymore, in the traditional sense. They're nanoparticles, little pieces of stuff, and they put them in superposition. The apparatus was called MUSCLE, short for Multi-Scale Cluster Interference Experiment. It was a 3-grating Talbot-Lowe interferometer, but instead of using physical gratings made of silicon nitride, it used ultraviolet laser beams to create the gratings optically. This is a crucial technical choice that goes back to the challenge of doing interferometry with massive particles. Here's the problem with physical gratings. When a large polarizable molecule passes through a narrow slit in a physical membrane, it interacts with the slit walls through van der Waals forces. These are weak electromagnetic attractions between the molecule and the material of the grating. For small molecules like C60, these forces are manageable. But as molecules get bigger and more polarizable, the van der Waals interactions get stronger, and they distort the interference pattern. Eventually, for large enough particles, the interactions with the grating walls would completely wash out the quantum signal. Physical gratings have a size ceiling. The solution which Arndt's group developed starting in 2007, is to replace the physical grating with a standing wave of laser light. The laser creates a pattern of bright and dark regions that acts as a phase grating for the particles. The particles interact with the light through the optical dipole force, which depends on their polarizability, and this interaction creates the periodic phase shift needed for interference. No walls, no van der Waals problems. The grating is made of light itself. The muscle interferometer uses 3 of these optical gratings in sequence, spaced about 10 centimeters apart. The first grating prepares spatial coherence in the beam of incoming particles. The second grating creates the diffraction. The third grating analyzes the resulting interference pattern. This 3-grating Talbot-Lau design is essential because it works with incoherent, extended particle sources. Unlike a standard double-slit experiment, which requires a nearly point-like source to produce coherent illumination, the Talbot-Lau setup accepts a broad, messy beam and still produces high-contrast interference fringes. The flux is thousands of times higher than far-field methods, which matters when you're trying to detect faint signals from rare particles. The sodium atoms were produced in a thermal source, heated until they evaporated, and then allowed to condense into clusters as the vapor expanded through a nozzle. The cluster sizes followed a natural distribution, peaked around 7,000 atoms, but ranging from about 5,000 to 10,000. The particles were cooled to 77 Kelvin, which is the temperature of liquid nitrogen, negative 196 degrees Celsius. The entire apparatus was held under ultra-high vacuum, around 9 times 10 to the negative 9th millibar. That's better than the vacuum of interplanetary space, and roughly 1,000,000 times better than a standard laboratory vacuum. The particles flew through the interferometer in about 1/100th of a second. During that time, the wave function of each particle spread out, passing through the optical grating in superposition, with the particle's center of mass simultaneously occupying positions separated by about 133 nanometers. That's the number that really lands. The particle itself was 8 nanometers across, and its superposition spread was 133 nanometers, more than 16 times its own diameter. If you scaled this up to something human-sized, it would be like a person being spread across a gap of about 30 meters, and the interference pattern appeared. Clear, unambiguous fringes with visibility up to 66% of the theoretical maximum. The quantum prediction matched. Classical physics could not explain the pattern. The fringes were there because each sodium cluster, each tiny blob of metal, had genuinely existed as a wave for the brief duration of its flight through the apparatus. But here's the number that matters most to physicists, and it's not the atom count or the mass. It's something called the macroscopicity parameter, designated by the Greek letter mu. This is a single number that captures how severely an experiment tests quantum mechanics against collapse theories. It accounts for the mass of the particle, the superposition separation, the coherence time, and the environmental isolation. A higher macroscopicity means a more demanding test. The 2026 experiment achieved a macroscopicity of 15.5. That doesn't sound impressive until you learn that this is an order of magnitude higher than any previous experiment in history. The 2019 molecule experiment scored about 14. Every other quantum superposition experiment, from atoms in traps to superconducting circuits, scored lower still. The sodium cluster result didn't just break the record, it smashed it. And there's a way to appreciate just how demanding this test is. To achieve an equivalently rigorous test of quantum mechanics using electrons instead of sodium clusters, you would need to maintain an electron in superposition for approximately 100 million years. The experiment accomplished in 1/100th of a second with heavy metal particles what would take 100 million years with the lightest particles available. Now I want to stop here and talk about what superposition actually means, because the popular framing of this is badly misleading. And if you're watching this channel, you deserve better than the standard pop science version. When people say the sodium cluster was in two places at once, they're using a shorthand that is convenient, but not quite right. It conjures an image of a particle that somehow exists as a physical object in location A and simultaneously as a physical object in location B. Two copies, two clumps of sodium, like a magic trick where something gets duplicated. That's not what happens. In quantum mechanics, a particle in superposition does not have a position at all. It's not that we don't know where it is, like losing your car keys. It's that the property called position genuinely is not defined for that particle in that state. The particle's quantum state is a mathematical object, a wave function, that assigns probability amplitudes to different possible locations. These amplitudes are not probabilities in the classical sense. They're complex numbers that can interfere with each other when the wave function has significant amplitude at two separate locations. We say the particle is in superposition of those locations. But what that means is that if you were to measure the position, you'd find the particle at one location or the other, with probabilities given by the squared magnitudes of the amplitudes. Before the measurement, the particle wasn't at either location. It wasn't anywhere. It was in a state that doesn't correspond to any definite position. This is not just philosophical hair-splitting. It has physical consequences. And the interference pattern is the proof. If the sodium cluster simply went through the grating at one position or another with classical probabilities, and we just didn't know which, then the detector would show a pattern corresponding to the sum of individual trajectories. No dark fringes, no interference, just a smooth distribution. The dark fringes, the places where particles almost never arrive, can only exist if the probability amplitudes from different paths cancel each other out. Destructive interference, amplitudes subtracting. This is a uniquely quantum phenomenon. Classical probabilities only add. They never subtract. You can never get fewer outcomes by considering more possibilities in classical statistics, but quantum amplitudes can be negative, or more precisely, they can be complex numbers with different phases, and when they add up out of phase, they cancel. So the dark fringes in the sodium cluster interference pattern are the proof. They are the empirical evidence that the cluster did not have a definite position as it traversed the interferometer. They are the physical record of a lump of 7,000 sodium atoms existing in a state where position was undefined, where the wave function encompassed multiple locations simultaneously, and where the resulting amplitudes interfered with each other. before the particle finally landed on the detector as a single dot. Every single sodium cluster arrived at one point, like a particle, but the pattern formed by thousands of them showed interference, like a wave. And this was not a gentle, marginal, barely detectable signal. It was 66% visibility, clean, strong, unambiguous. One more thing about the two places at once framing that's worth getting right. In a Talbot-Lowe interferometer, the superposition is not just two discrete locations, like the two slits in Young's experiment. The wave function is a continuous probability distribution that passes through the optical grating, picking up different phases at different positions. The 133 nanometers of superposition spread refers to the characteristic spatial scale over which the coherence of the wave function was verified. The particle's quantum state was spread over at least this distance, meaning that interference was observed between paths separated by this much. But the wave function itself was a smooth, continuous thing, not two sharp peaks. Saying two places at once captures the flavor, but not the full picture. This matters because it connects to a deep point about quantum mechanics. The theory doesn't actually tell you what's really happening between preparation and measurement. It gives you a mathematical object, the wave function, and a set of rules for calculating what you'll observe when you measure. What the wave function represents, what's really going on when nobody's looking, is the subject of a 100-year-old argument that shows no signs of resolution. And the Vienna experiments are directly relevant to that argument because different interpretations of quantum mechanics make different predictions about whether experiments like this should work at all. But that's getting into the territory of what this all means. The philosophy, the collapse theories, Penrose, the possibility that gravity itself enforces a boundary. Whether the quantum classical divide is real or just a practical limitation of our ability to isolate things from their environment. And to do that part properly, we need to talk about what actually destroys quantum superposition. What makes the interference pattern go away? Because the fact that the Vienna team can maintain coherence for 7,000 atoms at 77 Kelvin in a vacuum is not just a technical achievement. It's evidence about the nature of reality itself. And the thing it's evidence about is called decoherence. Decoherence is the reason you've never seen a cat in two places at once. It's the reason your coffee cup has a definite location. It's the practical explanation for why the world looks classical, even though the underlying physics is quantum mechanical. And understanding it is essential to understanding why the Vienna experiments are pushing at something genuinely fundamental. Here's the basic idea. Quantum superposition is fragile. If a particle in superposition interacts with its environment, if it bumps into an air molecule, absorbs a photon, emits thermal radiation, or in any way leaves a trace that carries information about its position, the superposition collapses. More precisely, the quantum coherence between the different paths leaks into the environment and becomes inaccessible to the experiment. The interference pattern washes out. The particle starts behaving classically. For an electron in a vacuum, decoherence can be slow because electrons are small and interact weakly with their environment. For a baseball, decoherence is essentially instantaneous. A baseball at room temperature emits trillions of thermal photons every second. each one carrying information about the baseball's position. The superposition would be destroyed in roughly 10 to the negative 30-something seconds, faster than any physically meaningful timescale. The baseball's wave function collapses before it's had time to spread by even a Planck length. This is not a limitation of our technology. This is a fact about the intensity of a macroscopic object's interaction with its thermal and electromagnetic environment. So the question of how big can you make a quantum superposition is really the question of how well can you isolate an object from its environment? And the answer depends on what you consider achievable isolation. The sodium clusters in the Vienna experiment were at 77 Kelvin. That's cold, but it's not ultra-cold by physics standards. Bose-Einstein condensates are created at temperatures of a few billionths of a degree above absolute zero. The sodium clusters were 9 orders of magnitude warmer than that. But that's okay, because the relevant temperature is the internal temperature of the particle relative to its tendency to emit thermal radiation. At 77 Kelvin, a sodium nanoparticle with 7,000 atoms emits very little infrared radiation over the 100th of a second it spends in the interferometer. Not zero, but little enough that the coherence survives. The vacuum helps enormously. At 9 times 10 to the negative 9th millibar, the mean free path between gas molecules is many meters. The sodium clusters fly through the interferometer without hitting any residual gas molecules. Each collision would destroy the superposition, so the vacuum has to be extremely good, and it was. Vibration isolation matters too. The optical gratings are created by laser beams, and if the laser setup vibrates relative to the particle beam, the interference fringes get smeared out. The apparatus sat on a multi-ton optical table floating on air cushions. All of this is engineering. Extraordinarily good engineering, operating at the limits of what current technology allows, but engineering nonetheless. The remarkable finding is that when you get the engineering right, when you genuinely isolate these 7,000 atom metal clusters from their environment, quantum mechanics works perfectly, with no sign of any breakdown. The theory predicts a specific fringe visibility, and the experiment delivers it. There is no mysterious force stepping in to collapse the wave function at this mass scale. There is no gravitational decoherence showing up in the data. There is no spontaneous localization mechanism leaving a detectable trace, which means one of two things. Either the mechanism that supposedly makes big things classical hasn't kicked in yet, because we haven't gone big enough, or there is no such mechanism, and the only thing that makes big things look classical is decoherence. The interaction with the environment, the constant measurement by the universe itself. This distinction is testable, and the Vienna experiments are the best tests we have. To understand why, you need to know about a thought experiment that was never meant to be taken literally, but has become the defining image of this entire problem. You need to know about the cat. In 1935, Erwin Schrödinger, one of the architects of quantum mechanics, published a paper in which he described a scenario designed to illustrate what he saw as an absurd consequence of the theory he had helped create. He asked you to imagine a cat sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives according to quantum mechanics, until someone opens the box and checks, the atom is in a superposition of decayed and not decayed. And since the cat's fate is linked to the atom, the cat should be in a superposition of alive and dead. Schrödinger didn't think the cat was actually in superposition. That was his point. He was arguing that something must prevent quantum superposition from scaling up to cats. The theory was clearly giving a wrong answer at the macroscopic level, and figuring out where it went wrong was, in his view, the central problem of quantum mechanics. 91 years later, we still don't have a definitive answer, but we have much better data. And the data consistently says that Schrödinger may have been wrong about the theory being wrong. Every time someone tests quantum mechanics at a larger scale, in a better isolated system, the theory holds. The interference pattern appears. The superposition persists. The cat, metaphorically speaking, stays both alive and dead. The sodium cluster experiment is the latest and most dramatic confirmation. 7,000 atoms, 170,000 atomic mass units, a mass comparable to a large protein or a small virus, existing in a quantum superposition of positions separated by more than 16 times the particle's own diameter. For roughly 10 milliseconds, this piece of metal did not have a location, and when it was detected, it obeyed the quantum prediction with high accuracy. That fact alone is striking. But the real significance lies in what it rules out, or rather, what it begins to rule out. Physics has several competing proposals for why the world looks classical. The standard view, which most working physicists implicitly adopt, is that decoherence explains everything. Big objects don't show quantum behavior because they interact so intensely with their surroundings that superposition is destroyed before it can produce observable effects. On this view, there is no fundamental boundary between quantum and classical. There is only a practical boundary set by how well you can isolate the system, improve the isolation, and you can push superposition to larger and larger objects without limit. But there are alternative proposals, and they're not cranks. They come from serious physicists who notice that the standard quantum formalism has a genuine logical gap. The theory tells you that systems evolve as superpositions according to the Schrödinger equation. It also tells you that when you measure a system, you get a definite result. These two rules are mathematically incompatible. The Schrödinger equation is deterministic and never produces collapse. Measurement outcomes are random and always involve collapse. Something has to give, and different physicists have different ideas about what. One of the most prominent alternatives comes from Roger Penrose, the Nobel Prize-winning mathematical physicist, best known for his work on black holes and general relativity. Penrose has argued since the late 1980s that gravity is responsible for wave function collapse. His reasoning goes like this. In quantum superposition, an object exists in two locations simultaneously. Each location corresponds to a slightly different arrangement of mass, and therefore a slightly different gravitational field. General relativity says that gravitational fields are the curvature of space-time. So a superposition of two locations is actually a superposition of two different space-time geometries. Penrose believes this is inherently unstable. Nature, he argues, cannot sustain a superposition of two incompatible spacetimes. The system must collapse to one or the other, and the timescale for this collapse depends on the gravitational self-energy difference between the two configurations. For an electron, the gravitational self-energy is so tiny that the predicted collapse time is around 10 million years. You'd never notice. For a kilogram mass object, the collapse time is about 10 to the negative 37th seconds. Instantaneous. And somewhere in between, for objects of about 10 to the negative 8th grams, roughly 22 micrograms, at the Planck mass scale, the collapse time is on the order of the experimental timescale. That's where the prediction becomes testable. The sodium clusters in the Vienna experiment weigh about 3 times 10 to the negative 19 grams. That is still roughly 14 orders of magnitude lighter than the Planck mass. So Penrose's theory does not predict that these clusters should fail to show superposition. They're still far too light. The experiment hasn't reached the regime where gravitational collapse should matter, but it's getting closer, and that getting closer is the whole point. Each order of magnitude in mass, each increase in macroscopicity, pushes the tested region further toward where Penrose and others predict things should break down, even though the sodium cluster result is fully consistent with standard quantum mechanics, which predicts no mass limit at all. It narrows the window for alternative theories. It tells us that if there is a collapse mechanism, it doesn't operate at the scale of 170,000 atomic mass units. Whatever is responsible for the classical appearance of the everyday world, it isn't kicking in at the scale of large proteins or small viruses. The other major alternative is the GRW model, proposed in 1986 by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. This is a mathematically precise modification of quantum mechanics in which wave functions spontaneously collapse at random without any measurement or environmental interaction needed. The collapse happens to individual particles at a very low rate, roughly once every 100 million years per particle. For a single electron, you'd never notice, but for a system with a huge number of particles, the collapses add up. If you have 10 to the 18th particles, about a microgram of matter, the expected time between collapses drops to milliseconds. This quickly forces the system into a definite state, making it behave classically. GRW is elegant because it smoothly interpolates between quantum and classical behavior. Small systems are quantum because collapses are rare. Large systems are classical because collapses are frequent. And the transition happens gradually, with a specific mathematical form that makes quantitative predictions. The Vienna experiments constrain the GRW model, but have not yet definitively tested it. The original GRW parameters predict a collapse rate of 10 to the negative 16th per particle per second, with a localization distance of about 100 nanometers. For a 7,000 atom sodium cluster, the expected collapse rate would be around 7 times 10 to the negative 13 per second. Over the 10 millisecond coherence time of the experiment, the probability of a spontaneous collapse would be about 7 times 10 to the negative 15. Negligible. The cluster is still too small and the experiment too brief for GRW to predict a detectable effect at the standard parameter values. However, the experiment does rule out variants of GRW with higher collapse rates or larger localization distances. The macroscopicity parameter of 15.5 means that any collapse model that would have disrupted this experiment is excluded, and that exclusion zone is an order of magnitude larger than what any previous experiment had achieved. So the situation is this. Standard quantum mechanics predicts no limit. Penrose and GRW predict limits, but at mass scales that current experiments haven't quite reached. The Vienna experiments are the closest anyone has come to reaching those scales. And every time they push further, the answer is the same. Quantum mechanics works. No collapse detected. The cat is still in superposition. Let me give you a sense of the scale comparisons here, because this is where it gets visceral. The 1927 Davis and Germer experiment showed interference with electrons. An electron weighs about 0.5 thousandths of an atomic mass unit. Call it half a thousandth of a Dalton. The 1999 buckyball experiment used C60 molecules weighing 720 Daltons. That's about 1.5 million times heavier than an electron. The 2019 oligoporphyrin experiment used molecules weighing 25,000 Daltons, about 35 times heavier than C60, about 50 million times heavier than an electron. The 2026 sodium cluster experiment used particles weighing about 170,000 Daltons, about 7 times heavier than the 2019 molecule, about 236 times heavier than C60, about 340 million times heavier than an electron. Over the course of a century, the mass of objects demonstrated in quantum superposition increased by a factor of roughly 340 million, and the quantum prediction held at every step without a single anomaly. Now consider the targets. A typical virus, like influenza, contains about 10 million atoms and weighs around 40 million Daltons. That's about 235 times heavier than the current record. A small bacterium like mycoplasma contains roughly 10 billion atoms. A red blood cell, about 10 to the 13th atoms. A grain of sand, about 10 to the 20th atoms. Your body, about 10 to the 28th atoms. The distance between the current record and a virus is roughly a factor of 200. The distance between a virus and a bacterium is roughly a factor of 1,000. The distance between a bacterium and a human is roughly a factor of 10 to the 17th. Each step gets exponentially harder because larger objects interact more strongly with their environments and are exponentially more difficult to isolate. But the interesting targets aren't at the human scale. They're in the next few orders of magnitude above current records, because that's where the predictions of Penrose, GRW, and standard quantum mechanics start to diverge. If you could put a virus in superposition, you'd be testing quantum mechanics at a scale where some collapse models predict it should fail. If you could put a small mirror or a micro-mechanical oscillator in superposition at the scale of micrograms, you'd be testing Penrose's gravitational collapse directly. These experiments are being designed right now. They are the next frontier, and the Vienna result is the launchpad. There's one more aspect of the 2026 experiment that deserves attention, and it's about what kind of object was used. Every previous large molecule interference experiment used a specific chemical compound. One molecule, one formula, one structure. The 2019 experiment used a molecule with a precise chemical composition, synthesized by chemists in Basel. purified and characterized with known optical and thermal properties. It was, in every sense, a designer molecule. The sodium clusters are different. They're not molecules. They don't have a fixed composition. A cluster of 7,000 sodium atoms is just a blob of metal. Its exact structure depends on how it formed, and each cluster in the beam is slightly different from its neighbors. Some have 6,800 atoms. Some have 7,200. The distribution is broad and natural, not precisely controlled. This matters for two reasons. First, it demonstrates that quantum interference does not require the exquisite precision of single molecule chemistry. You can take a fundamentally messy, naturally formed particle and show that it behaves quantum mechanically. This suggests that the quantum classical boundary, if it exists, does not depend on the internal structure or complexity of the object. It depends on mass, isolation, and coherence time. Nothing else. Second, nanoparticles are easier to scale up than custom molecules. You don't need a world-class synthetic chemistry lab to make bigger particles. You just need better sources, better cooling, and better vacuum. The path from 7,000 atom sodium clusters to 100,000 atom clusters or million atom clusters is an engineering challenge rather than a chemistry challenge. It's still ferociously difficult engineering, but it's a fundamentally more scalable approach than synthesizing ever larger designer molecules. Arndt and his team have been explicit about this. The muscle apparatus was designed to accommodate larger particles. The optical gratings can, in principle, work with masses far beyond what's been tested. The primary limitations are source technology, cooling to suppress thermal radiation, and vacuum quality. All of these are active areas of development. The 2026 result is not the end of the road. It's the beginning of a new one. Sebastian Pedalino, the lead author on the 2026 paper, put it simply. Intuitively, one would expect such a large lump of metal to behave like a classical particle. The fact that it still interferes shows that quantum mechanics is valid even on this scale and does not require alternative models. And then, with the understatement typical of experimental physicists, he added that the result opens the door to testing the limits of quantum mechanics in an entirely new regime. That new regime is what we need to talk about next. The proposals for space-based experiments, the plans to put mirrors, glass beads, and possibly even living organisms in superposition, the theoretical predictions about where, if anywhere, quantum mechanics should finally break down, and the unsettling possibility that it never does, that the laws governing 7,000 sodium atoms are exactly the same laws governing you and me and every object in the universe. And the only reason we don't see ourselves in two places at once is that the universe itself is constantly watching. But before we get there, there's something worth pausing on. The sheer technical achievement of what happened in that Vienna laboratory, because the numbers I've been throwing around might make it sound routine. It was not routine. Let me walk you through what had to go right simultaneously for this experiment to work. Start with the source. You need to produce sodium nanoparticles in the gas phase, in a vacuum, with a reasonably narrow size distribution, flying at a known velocity, in a directed beam. Sodium is a reactive alkali metal. It burns in air. It explodes in water. At room temperature, it's a soft, silvery solid. To make nanoparticles, You heat it until it evaporates. Then let the vapor expand through a nozzle into vacuum. As the vapor cools during expansion, atoms start sticking together, forming clusters. The size distribution depends on the temperature, the nozzle geometry, the pressure, and the expansion rate. Getting clusters peaked around 7,000 atoms with a usable flux took years of source development. Now those clusters are flying through your apparatus at roughly 100 meters per second. They're still warm. A 7,000 atom sodium cluster at 77 Kelvin has significant thermal energy, and it's constantly trying to shed that energy by emitting infrared photons. Every photon it emits carries information about its position. If the cluster emits even a single photon with a wavelength shorter than the superposition separation, the coherence is destroyed. The witch path information has leaked into the environment. Game over. No interference. This is why the cooling matters. At 77 Kelvin, the peak thermal radiation wavelength is about 38 micrometers, which is roughly 38,000 nanometers. That's much longer than the superposition separation of 133 nanometers. So the thermal photons don't carry enough spatial resolution to reveal which path the cluster took. The cluster can radiate without destroying its own coherence, but only barely. Push the temperature higher or the coherence time longer, and the thermal photons start to matter. There's a narrow window where this works, and the Vienna team found it. The vacuum is the next challenge. At 9 times 10 to the negative 9th millibar, there are still residual gas molecules in the chamber, mostly hydrogen. If a single gas molecule collides with the sodium cluster during its flight through the interferometer, the collision transfers momentum, and the recoiling gas molecule carries information about the cluster's position. Coherence destroyed. The mean free path at this vacuum level is hundreds of meters, far longer than the interferometer, so collisions are rare. But rare is not never. Run the experiment 10,000 times, and you need collisions to be rare enough that the interference signal isn't washed out by the fraction of clusters that did get hit. Then there are the laser gratings, 3 standing waves of ultraviolet light, each one precisely aligned, with periods of about 100 nanometers. The period has to be stable to better than a nanometer over the course of the experiment. Any vibration in the laser mounts, any thermal drift in the optical table, any fluctuation in the laser frequency smears the fringes. The apparatus uses active stabilization, feedback loops that monitor the grating positions and correct for drift in real time. This level of precision is comparable to what's used in gravitational wave detectors like LIGO, applied to a tabletop experiment. And finally, detection. The sodium clusters that make it through the interferometer need to be detected individually, with spatial resolution better than the fringe spacing. The team used surface ionization detection, where clusters hitting a hot wire lose an electron and become ions that can be counted and position mapped. The detection efficiency has to be high enough to build up statistics in a reasonable time, and the spatial resolution has to be fine enough to resolve the interference fringes. Every single one of these subsystems had to work simultaneously at the edge of its performance envelope for the experiment to succeed. Source, cooling, vacuum, laser gratings, stabilization, detection. A failure in any one of them would destroy the quantum signal. The fact that it all came together is a testament to 25 years of accumulated expertise in Arndt's group. They didn't just walk into the lab one day and try this. They built toward it through decades of incremental improvements, each one making the next step possible. This is what big science looks like in experimental quantum physics. It's not particle accelerators and 1,000-person collaborations. It's a team of maybe a dozen people in Vienna, pushing the limits of tabletop physics with equipment they largely built themselves, testing the foundations of quantum theory 1 nanometer at a time. And now, consider what they found. After all that effort, after years of development and engineering at the limits of what's achievable, the result was exactly what the textbook said it should be. Quantum mechanics predicted a specific interference pattern for sodium clusters of this mass at this temperature, with these grating parameters in this vacuum. And the experiment produced that pattern. Visibility 66%. Predicted visibility, given the known experimental imperfections, about 66%. No anomaly, no deviation, no sign of any breakdown. The same theory that describes an electron orbiting a hydrogen atom also describes a 7,000 atom metal cluster flying through a laser grating. The math doesn't care about the size, it just works. This is both reassuring and deeply strange. Reassuring because quantum mechanics is our most precisely tested theory. It has been confirmed to more than 10 decimal places in some measurements. Finding that it works at a new scale is, in one sense, exactly what you'd expect from a successful theory. You'd be far more shocked if it didn't work. But strange, because of what the theory actually says. It says this 7,000 atom blob of metal did not have a location for 10 milliseconds. It says the blob's center of mass was spread across a gap larger than itself. It says the blob interfered with itself, producing cancellations that require probability amplitudes from different spatial locations to combine destructively. And it says there is nothing in the mathematical structure of the theory that prevents this from happening to bigger and bigger objects, all the way up to cats, people, planets, and the universe itself. The theory says the classical world is a mirage, an approximation that works because you're big and warm and constantly interacting with everything around you. But an approximation nonetheless. And every time the Vienna team makes that approximation harder to justify at the boundary, the world shrugs and continues being quantum. That is the significance of the 2026 result. Not that it surprised anyone who trusts quantum mechanics, but that it extends the domain of verified quantum behavior into a regime where, for the first time, the particle is something you might reasonably call a thing, not a molecule, not a carefully designed chemical structure, a piece of stuff, a nanoparticle, a speck of metal that you could, with a good enough electron microscope, actually photograph 7,000 atoms in 2 places at once, or more precisely, 7,000 atoms with no place at all, for 1/100th of a second in a laboratory in Vienna. And if you want to understand what that means for reality, for the deepest question physics has ever asked, for whether the universe is fundamentally classical with quantum footnotes or fundamentally quantum with classical appearances, then you need to know what happens next. The experiments that are being planned right now in laboratories and space agencies around the world to push this boundary further than anyone thought possible a decade ago. That's where this gets really interesting. Think about the trajectory. In 1927, Davison and Germer showed that electrons diffract. Electrons weigh about 0.005 of an atomic mass unit. It took 72 years until 1999 for anyone to demonstrate the same thing with an object weighing 720 Daltons. Then the pace accelerated. 20 years from C60 to the 25,000 Dalton oligoporphyrin. 7 more years to the 170,000 Dalton sodium cluster. The mass has been increasing roughly tenfold every decade for the past quarter century. If that trend continues, and there's no fundamental reason it shouldn't, within a decade, experiments could reach the megadalton range, the mass of a small virus. Within 2 decades, the 100 megadalton range, the mass of a large virus or a very small organelle. At some point in that range, the predictions of standard quantum mechanics and the predictions of gravitational collapse models start to diverge, not subtly, definitively. And that is the prize, not just confirming that quantum mechanics works, again, at a slightly larger scale, but finding out whether it fails. Because a failure of quantum mechanics at some mass threshold would be one of the greatest discoveries in the history of science. It would mean new physics. It would mean that gravity and quantum mechanics interact in ways we don't currently understand. It would crack open a door that has been locked since the 1930s, when people first noticed that our 2 best theories of physics, quantum mechanics, and general relativity are mathematically incompatible. The Vienna experiment hasn't found that failure. Not yet. What it has done is push the boundary further than anyone else, establish the experimental tools and techniques needed to keep pushing, and demonstrate that quantum mechanics continues to work flawlessly at a scale where many physicists, including some very good ones, had a reason to think it might not. The cat remains in superposition, and the box is still closed, but someone is working on opening it. So let's talk about what's actually at stake. Not just experimentally, but philosophically, because the Vienna result lands in the middle of an argument that has been running since the late 1920s, and it's an argument that most physicists would rather not have in public. It touches on what physics is actually for, whether the job of a theory is to describe what you measure or to tell you what's really going on. Quantum mechanics, as it's taught in textbooks, has 2 rules. Rule 1 is the Schrödinger equation. It tells you how the quantum state of a system evolves over time. It's deterministic, meaning if you know the state now, you can calculate the state at any future time with perfect precision. It's also linear, meaning if the system can be in state A and it can be in state B, it can also be in any combination of A and B, a superposition. The Schrödinger equation never collapses superpositions. It only creates them and elaborates them. Left to its own devices, it would put the entire universe into one enormous, ever-branching superposition of every possible configuration of every particle. Rule 2 is the measurement postulate. It says that when you measure a quantum system, you get a definite result, not a superposition. One outcome, and the probability of each possible outcome is given by the square of the corresponding amplitude in the wave function. After the measurement, the system is in whatever state corresponds to the result you got. the superposition is gone, collapsed. These two rules contradict each other. Rule 1 says superpositions grow and never collapse. Rule 2 says measurements cause collapse. But measurement is not defined anywhere in the formalism. There's no equation for it. There's no physical criterion that says when Rule 1 stops applying and Rule 2 takes over. The theory just says, evolve the system according to the Schrodinger equation until you measure it, then use the measurement postulate. But it never tells you what counts as a measurement. This is the measurement problem. It has been called the most important unsolved problem in physics, and different answers to it lead to radically different pictures of reality. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg in the late 1920s, essentially sidesteps the problem. It says that quantum mechanics is a tool for predicting measurement outcomes, and that's all it is. Don't ask what's really happening between measurements. The question is meaningless. The wave function isn't a physical thing. It's a mathematical device for calculating probabilities. When you measure, you get a result. That's the physics. Everything else is philosophy. This has the virtue of being operationally clear. It tells you exactly how to use the theory to make predictions, and those predictions are spectacularly accurate. It has the disadvantage of being deeply unsatisfying to anyone who thinks physics should describe reality, not just predict experiments. And it offers no explanation whatsoever for why measurements are special. What distinguishes a measurement from any other physical interaction, or where the quantum classical boundary lies? The many-worlds interpretation, proposed by Hugh Everett in 1957, takes the opposite approach. It says the Schrodinger equation is the whole story. There is no collapse, ever. When a quantum system interacts with a measuring device, the system and the device and the observer all go into superposition together. The universe branches. In one branch, you see outcome A. In another branch, you see outcome B. Both branches are equally real. You just happen to be in one of them. Many worlds is mathematically elegant. It requires no additional postulates beyond the Schrodinger equation. It solves the measurement problem by dissolving it. But it comes at a staggering ontological cost. It says reality consists of a continuously branching tree of parallel universes, the vast majority of which are forever inaccessible to us, and it provides no experimental way to test whether these other branches exist. You might find that price too high. Many physicists do. Pilot wave theory, developed by Louis de Broglie and later elaborated by David Bohm, says that particles always have definite positions. They are guided through space by a pilot wave, which is the wave function, and the pilot wave evolves according to the Schrodinger equation. The particle surfs the wave. In the double-slit experiment, the particle goes through one slit, but the pilot wave goes through both, and the wave's interference pattern guides the particle to the bright fringes and away from the dark ones. This recovers all the predictions of standard quantum mechanics while maintaining that particles are always somewhere definite. The catch is that pilot wave theory is explicitly non-local. The pilot wave is a function defined over the entire configuration space of the universe, and a change in one part of it can instantaneously affect a distant particle's trajectory. Einstein would not have approved. Also, in its standard formulation, pilot wave theory makes exactly the same predictions, as Copenhagen and many worlds for all currently feasible experiments. It can't be distinguished from them by any measurement we know how to do. This is the frustrating reality of the interpretations debate. Copenhagen, many worlds, and pilot wave theory all make identical predictions for every experiment that has ever been performed or proposed. They disagree about what's happening behind the curtain, but they agree on every number that comes out of the apparatus. The debate is, in a strict empirical sense, scientifically undecidable unless you change the theory. And this is why Penrose and GRW matter. They don't just offer different interpretations of quantum mechanics. They offer different theories, modified versions of quantum mechanics that make different predictions from the standard theory. Predictions that can, in principle, be tested. We touched on Penrose's gravitational collapse earlier, but let me give you the full picture, because the logic is beautiful even if the conclusion turns out to be wrong. Start with general relativity. In Einstein's theory, gravity is not a force. It's the curvature of space-time caused by the presence of mass and energy. The sun doesn't pull the Earth toward it. The sun curves the space-time around it, and the Earth follows the straightest possible path through that curved space-time, which happens to be an ellipse. Mass tells space-time how to curve. Space-time tells mass how to move. Now put a massive object in quantum superposition. Say the object is in a superposition of being here and being there, with some distance between the two locations. Each location corresponds to a different distribution of mass. Each distribution of mass corresponds to a different curvature of space-time. So the superposition of positions is really a superposition of space-time geometries. Two different shapes of the universe coexisting. Penrose argues that this is fundamentally untenable. General relativity is a theory of one space-time. It doesn't have the mathematical machinery to handle two spacetimes superposed on top of each other. The very concept of time becomes ambiguous because the time coordinate in one geometry doesn't match the time coordinate in the other. According to Penrose, this ambiguity creates an instability. Nature resolves it by collapsing the superposition to one geometry or the other, and the timescale for the collapse is set by the gravitational self-energy of the superposition, roughly the energy it would take to move the mass from one location to the other through its own gravitational field. For small objects like electrons, this energy is infinitesimal. The collapse time is millions of years. Quantum mechanics proceeds essentially unmodified. For large objects like cats or people, the energy is enormous. The collapse is essentially instantaneous. Classical behavior emerges automatically, and for objects in between, in the range of nanograms to micrograms, the collapse time is measurable, seconds, milliseconds. This is the testable regime. The 2026 sodium cluster experiment sits well below this regime. At 170,000 Daltons, the gravitational self-energy of the superposition is so tiny that Penrose's predicted collapse time would be vastly longer than the age of the universe. The experiment cannot test Penrose's specific prediction, but it pushes toward it. And if the experimental mass can be increased by 4 or 5 more orders of magnitude, which is the goal of the next generation of experiments, the test becomes direct. GRW, the spontaneous collapse model, operates differently. It doesn't invoke gravity. It simply postulates that wave functions randomly collapse at a fixed rate per particle. The original parameters, a collapse rate of about 10 to the negative 16th per nucleon per second, and a localization distance of about 100 nanometers, were chosen specifically to be undetectable for microscopic systems, but effective for macroscopic ones. A single nucleon collapses on average once every 100 million years, but a mole of nucleons, about 6 times 10 to the 23rd particles, experiences roughly 6 times 10 to the 7th collapses per second. That's 60 million spontaneous localizations every second, more than enough to force the system into a definite state almost instantly. The beauty of GRW is that it's quantitative. It gives you a formula. You can calculate for any given object in any given superposition how long the coherence should last, and you can compare that calculation to what the experiment shows. If the experiment shows coherence lasting longer than GRW predicts, the model is wrong, or at least the parameters need to be adjusted. The sodium cluster experiment doesn't quite reach the original GRW parameters. The clusters are too small and the coherence time too short for the standard collapse rate to produce a detectable effect. But the experiment does exclude modified versions of GRW with higher collapse rates. The macroscopicity value of 15.5 quantifies exactly how much parameter space has been ruled out, and each future experiment that pushes the macroscopicity higher squeezes the remaining parameter space further. This is the real scientific value of the Vienna program. Not confirming quantum mechanics, which everyone expects, but constraining the alternatives, narrowing the space of possible collapse mechanisms, putting tighter and tighter bounds on any theory that says superposition should fail above some mass scale. If quantum mechanics is going to break down, these experiments are telling us exactly where it hasn't broken down yet, and the yet keeps moving. So what comes next? Where does this program go from here? There are several proposals on the table, ranging from ambitious to borderline audacious. The most developed is MACRO, which stands for macroscopic quantum resonators in space. This is a proposal that has been submitted to the European Space Agency multiple times since 2010, most recently in 2024. The idea is to perform matter wave interferometry in space using silica nanospheres with masses up to 10 to the 11th atomic mass units. That's 100 billion Daltons, about 600,000 times heavier than the current record. Space offers 3 things that Earth doesn't. First, microgravity. On Earth, particles fall under gravity during the experiment, which limits the coherence time because the particles drop out of the interferometer. In orbit, at the L2 Lagrange point, there's no gravitational acceleration to worry about. The particles can float freely for 100 seconds or more, compared to a fraction of a second on the ground. Second, vacuum. The residual gas pressure at L2 is below 10 to the negative 14th pascals, many orders of magnitude better than the best laboratory vacuum on Earth. Fewer gas molecules means fewer collisions, means longer coherence. Third, thermal isolation. In deep space, far from the Earth's thermal radiation, the cryogenic environment is naturally maintained. MACRO is not funded yet. It's been reviewed by ESA and ranked as scientifically interesting but technically challenging. A Pathfinder mission using CubeSat-scale hardware has been proposed for the late 2020s to demonstrate the key technologies in orbit before committing to the full experiment. If it works, the full mission could fly sometime in the 2030s. If Macro reaches its target mass, it would directly test both GRW and Penrose in regimes where they make different predictions from standard quantum mechanics. 100 billion Daltons is still below the Planck mass, but it's close enough that Penrose's gravitational collapse would predict measurable effects on the coherence time. A positive detection of collapse would be one of the biggest discoveries in the history of physics. A null result showing that quantum mechanics continues to hold would rule out both theories in their standard formulations. Closer to Earth, literally, there's Dirk Baumeister's mirror experiment. Baumeister, a physicist at the University of California, Santa Barbara, and Leiden University in the Netherlands, is building an experiment to put a tiny mirror in superposition. The mirror is about 50 micrometers across, which is roughly the width of a human hair, and contains about 10 to the 14th atoms. The idea is to use a single photon split into a superposition of taking two paths to push the mirror into a superposition of two positions. If the photon takes path A, it bounces off the mirror and gives it a tiny kick one way. If it takes path B, it gives the mirror a tiny kick the other way. Since the photon is in superposition of both paths, the mirror should end up in superposition of both positions. At 10 to the 14th atoms, this mirror would be in the mass range where Penrose's theory predicts collapse within about 1 second. The experiment would directly test whether a massive object placed in superposition by quantum mechanical means stays in superposition, as standard quantum mechanics predicts, or spontaneously collapses, as Penrose predicts. Baumeister has said publicly that he expects results within 3 to 5 years, though experimental physicists' timelines should always be taken with some caution. And then there's the most provocative proposal of all, putting a living organism in superposition. In 2010, a team of theorists led by Oriol Romero-Isard published a proposal for placing a virus in quantum superposition using an optical cavity. The candidate organisms include influenza virus, which is roughly 100 nanometers in diameter and contains about 10 million atoms, and tobacco mosaic virus, which is a rod-shaped virus about 50 nanometers wide and up to 300 nanometers long. Both can survive in vacuum for extended periods. The proposal uses a technique called cavity optomechanics. You trap the virus in the standing wave of light inside an optical cavity, cool its center of mass motion to the quantum ground state, and then create a superposition by manipulating the trapping potential. The technical challenges are formidable. You need to cool the virus's center of mass motion to near absolute zero while keeping its internal structure intact. You need vacuum good enough to prevent decoherence for the duration of the experiment. And you need to confirm that the virus is still viable afterward to ensure that you genuinely put a living thing in superposition, not just a dead clump of proteins. Nobody has done this yet. The gap between the current record and virus-scale superposition is about 200 to 1,000-fold in mass, but that gap was similar in scale to the gap between C60 and the 2019 oligoporphyrin, and the Vienna group closed that gap in 20 years. There is no fundamental physical barrier to putting a virus in superposition. There is only engineering. Whether a virus in superposition would be in two places at once in any meaningful biological sense is a philosophical question that physicists tend to avoid. The virus wouldn't be conscious of its predicament. It wouldn't experience being in two locations. Its center of mass would lack a definite position, and that's all the physics says. But the image of a living thing, something that metabolizes and reproduces and evolves, existing in a quantum superposition, is powerful enough to have driven an entire research program. And if it works, it won't stop at viruses. The next target would be bacteria, then tardigrades, the microscopic animals that can survive in the vacuum of space, in temperatures near absolute zero, in pressures that would crush a submarine. Tardigrades are about 0.5 millimeter long and contain roughly 10 to the 17 atoms. Putting a tardigrade in superposition is, today, in the realm of fantasy. But 25 years ago, so was putting 7,000 sodium atoms in superposition. And here we are. Let me circle back to where we started. A team of physicists in Vienna took a clump of sodium metal containing roughly 7,000 atoms and demonstrated that it behaves as a quantum wave. Its position was undefined. Its wave function spread across a gap 16 times wider than the particle itself. The interference pattern was clean and matched quantum predictions with no deviation. This is not a fringe result from an obscure laboratory. It was published in Nature, the most prestigious scientific journal in the world, by a group led by Marcus Arndt, who has spent 25 years systematically pushing the limits of quantum superposition. It builds on a lineage that traces directly back to the foundational experiments of quantum mechanics. Davison and Germer, de Broglie, Schrödinger, Feynman's only mystery, the double-slit. Every step in that lineage has confirmed the same uncomfortable truth. Quantum mechanics works. The wave function is real, or at least it makes correct predictions. And the classical world we see around us is not fundamental. It's emergent. It's what you get when quantum systems interact with their environments so intensely that the superpositions become undetectable. But they're still there, under the surface. The question is whether they're always there, whether quantum mechanics is truly universal, or whether something, gravity, spontaneous collapse, some physics we haven't imagined yet, forces a transition to classical behavior above some mass threshold. The 2026 experiment doesn't answer that question, but it narrows the window. It tells us that if the transition exists, it doesn't happen at 170,000 Daltons. It doesn't happen at the scale of large proteins. It doesn't happen at the scale of nanoparticles you could image in an electron microscope. It might happen at the scale of viruses, or bacteria, or mirrors, or it might not happen at all. 91 years after Schrödinger put his cat in a box, the cat is still in superposition. The box has gotten smaller, the instruments have gotten sharper, and the fringes keep appearing, dark bands in a pattern of dots, where particles never land because their quantum selves cancelled out. Every dark fringe is a whisper from reality, saying something that human intuition desperately does not want to hear. You are made of quantum stuff. The rules that govern 7,000 sodium atoms govern the 10 to the 28th atoms in your body. The only reason you have a definite location, the only reason you exist as a single version of yourself in a single place at a single time, is that the universe is watching you. Every photon bouncing off your skin, every air molecule bumping against you, Every thermal vibration in your cells is a measurement, collapsing your superposition before it can spread by even a trillionth of a meter. You are classical because you are observed constantly by everything. The sodium clusters in Vienna were classical too, until the physicists stopped the universe from watching. They cooled them. They evacuated the air. They shielded them from photons. And in that brief window of isolation, the metal remembered what it really was. A wave. Something with no position. Something spread across space. Something that interfered with itself and left the proof in the pattern of dots on a detector. The physicists opened a tiny gap in the curtain of decoherence, and quantum reality peeked through. 7,000 atoms wide. Next time, it'll be wider. There's one thread I've left hanging, and it's the one from the title. The claim that nobody is talking about this. That's not entirely fair. The 2026 result was covered by Nature News, by Live Science, by phys.org, by a handful of other science outlets. If you follow quantum physics publications, you heard about it. But compare the level of attention to other recent physics milestones. When LIGO detected gravitational waves in 2016, it was front-page news worldwide. When the Event Horizon Telescope produced the first image of a black hole in 2019, the picture was everywhere. Those results received the full treatment. Press conferences, magazine covers, trending hashtags, late-night television segments. The sodium cluster result did not. And you could argue that's reasonable. Gravitational waves and black hole images have more visual drama. They're easier to explain in a headline. Scientists detect ripples in spacetime is a more immediate hook than metal nanoparticle shows quantum interference. But in terms of what they tell us about the fundamental nature of reality, the Vienna experiment is arguably more profound. Gravitational waves confirmed a specific prediction of general relativity. Important, but expected. The black hole image was spectacular, but it too confirmed what theory had predicted for decades. The Vienna experiment confirms quantum mechanics, yes, but it does something more. It extends the domain of confirmed quantum behavior into a regime that was, until very recently, purely theoretical. It puts direct experimental pressure on competing theories of wave function collapse. It advances a research program whose ultimate endpoint, if pursued to its logical conclusion, is answering whether the universe is fundamentally quantum or fundamentally classical. That is not a small question. It might be the biggest question physics has. And yet, 7,000 atoms in superposition, and most people will never hear about it. Partly, that's because the result is hard to visualize. There's no photograph to show, no sound to play. The interference pattern is a graph of dot positions, a histogram of where particles landed. It's not cinematic, but it is, in the quietest possible way, one of the most radical experimental findings of the 21st century. The researchers themselves don't oversell it, and that's to their credit. Physicists in Vienna have been doing this work for a quarter century, and they've developed the kind of restrained confidence that comes from knowing exactly what your data says and exactly what it doesn't. They publish in top journals. They present at conferences. They write papers with titles like Probing Quantum Mechanics with Nanoparticle Matter Wave Interferometry. They do not write press releases that say, "Scientists prove reality is a lie." But maybe reality isn't a lie. Maybe it's something stranger. Maybe reality is a vast quantum superposition, and the definite, solid, single-outcome world you experience is just what it looks like from inside one branch. Or maybe reality is a continuous wave function with no branches at all, and particles surf through it on hidden currents. Or maybe the wave function is just a calculation tool, and the question of what's real doesn't have a quantum answer. What the Vienna experiments give us is not a philosophical resolution. It's data, hard, clean, unambiguous data about where quantum mechanics holds and where it might not. And right now, after a century of checking, it holds everywhere we've looked. The theory that Schrödinger himself thought must be incomplete. The theory whose implications drove Einstein to spend the last 3 decades of his life searching for an alternative. The theory that Feynman said nobody truly understands continues to pass every test at every scale. 7,000 atoms, 170,000 Daltons, 8 nanometers of metal, spread across 133 nanometers of space. No position, no definite location, just a wave interfering with itself, leaving dark fringes in its wake. This happened in January 2026 in a laboratory at the University of Vienna on an optical table mounted on air cushions inside a vacuum chamber with better than interplanetary emptiness, cooled to the temperature of liquid nitrogen. A team of scientists spent 25 years building toward this moment, and when it came, the result was exactly what quantum mechanics predicted. No surprise, no anomaly, no boundary between quantum and classical, just fringes. And in those fringes, if you know what you're looking at, is the shape of a question that physics has been asking since 1935. Schrodinger's question. The question about the cat. The question about whether the rules that govern atoms also govern everything made of atoms. The question about whether the universe is, at bottom, as definite as it appears. The fringes say no, the universe is not definite. The definiteness is local. It's contextual. It emerges from interaction, not from fundamental law. And the sodium clusters proved it briefly in a chamber in Vienna before the universe noticed them again and pinned them back into being ordinary lumps of metal with ordinary positions in ordinary space. For 1/100th of a second, they escaped. They were waves. They were everywhere and nowhere. And then there were particles again, landing on the detector, one dot at a time, building a pattern that shouldn't exist if the world is what it seems. 7,000 atoms, 2 places, nobody talking about it. Now you are. One final thought. About the people, Anton Zeilinger, who supervised the original 1999 buckyball experiment, won the 2022 Nobel Prize in Physics, but not for the molecule work, for quantum entanglement. The Nobel Committee recognized his experiments proving that entangled particles violate Bell inequalities, confirming that quantum correlations are genuinely non-local and not explained by hidden variables. It was richly deserved. But there's an irony in the fact that Zeilinger's other major contribution, the program of macromolecule interferometry that he co-founded with Anton, is arguably closer to answering the deepest question in quantum foundations. And it wasn't what Stockholm chose to honor. Zeilinger, now in his 80s, remains philosophical about the mysteries he spent a lifetime probing. He once said that some of the fundamental questions, the very question of what quantum mechanics really means, remain in a basic way unanswered. That's not false modesty. It's an honest assessment from someone who has done as much as anyone alive to test the theory empirically. Marcus Arndt, who took the molecule program and ran with it after Zeilinger shifted focus to entanglement, has spent his entire career in this one lane. He joined Zeilinger's group in 1997, specifically to do macromolecule interferometry. He ran the C60 experiment. He built the KDTLI. He pushed through every mass milestone from 720 Daltons to 170,000. He won Austria's Wittgenstein Prize, the country's highest research honor, in 2008. He holds an ERC advanced grant, and he has stayed in Vienna the entire time, building one of the most focused and productive experimental programs in quantum physics. There's something admirable about that level of commitment to a single question. While other physicists chase whatever topic is trending, Arndt has spent a quarter century asking the same thing. How big can you make a quantum superposition? And then building the apparatus to find out. The answer keeps coming back the same. Bigger than last time. No sign of stopping. Marcel Meyer, the chemist in Basel who synthesized the designer molecules for the 2011, 2013, and 2019 experiments, deserves recognition too. Without his custom molecules, the intermediate mass range between buckyballs and nanoparticles would have been inaccessible. Physics and chemistry working together, each enabling what the other couldn't do alone. The 2026 shift to sodium nanoparticles reduces the dependence on custom synthesis, but the molecular experiments established the scientific foundations and developed the interferometry techniques that made the nanoparticle work possible. These are not household names. They will probably never be household names, but the question they're answering is as fundamental as anything in physics, and the care and precision they bring to it is extraordinary. 25 years of work, building toward 10 milliseconds of metal not having a position. That ratio of preparation to phenomenon is almost absurd, but that's what it takes to peer behind the curtain of decoherence. The curtain that separates the quantum world you know must exist from the classical world you experience every second of your life. The Vienna team has pulled it back further than anyone before them. Not all the way, not yet, but further. And behind it, every time, they find the same thing: waves.